So now we're going to look at sketching the graph of a rational function, a ratio of two polynomials. And these graphs can get really interesting because the functions have denominators. So there are certain critical values that x can't be. And we're going to need to investigate what happens near those critical values. We also need to look at the end behavior and the middle behavior. I'll show you how to do this with a calculator, and I'll also show you how to do it with the leading term and to get the end behavior and use the multiplicities of the critical values. Let's get started. So let's sketch the graph using end behavior and a sign chart. So our first function is going to be pretty involved because this is the one I'm going to do on the calculator to show you all the different things that can happen. So on top, we've got negative x squared times x plus 1 times x minus 5. And on bottom, we've got 3x plus 2 times x minus 5. And the first thing you might notice in this rational function is that x minus 5 looks like it will cancel. And it does. But when you cancel it, you can't pretend like it never existed, because right now you can see that x can't be 5, because if you plug in 5, you'll have a 0 on the bottom. You'll be dividing by 0. So I'm not going to cancel it. I'm going to leave it there so we can see what happens at that x value. One nice thing about this particular function, though, is it is factored for us. So we can go ahead and generate our sign chart and mark our zeros and critical values. So we have 5 of them, or 4 of them, it looks like. We've got 0 with multiplicity 2, negative 1, multiplicity 1. Positive 5 has multiplicity 2 because x minus 5 shows up twice. And if we set 3x plus 2 equal to 0, we can see that x would be negative 2/3, and that's multiplicity 1. So it looks like negative 1 is our first critical value, multiplicity 1. And if x is negative 1 and we plug it in, it makes the numerator 0, which makes the whole fraction equal to 0. So for the x value of negative 1, the output y is 0. Then we've got negative 2/3 is next, and its multiplicity is 1. Now, if we plug in negative 2/3, that's going to make the denominator 0, which means the whole function is undefined. So I'll just put a u there. And we'll need to investigate what happens near that particular critical value. Then we have, let's see, 0, multiplicity 2. And since it makes the numerator 0, the function is going to output 0. And then finally, we have 5, which is also multiplicity 2. If we plug in 5, it makes the numerator and denominator 0, but you can't divide by 0, even if the numerator is 0. So this is also going to be undefined. So now what we want to do is we need to do a lot of work here with the calculator. Now, when I say a lot of work, the calculator does all the work. The rest is pretty easy for us. So we need to investigate what happens in each of these regions. So we're going to pick test points for each of the regions. Maybe over here we'll pick like negative 1,000. Maybe between negative 2/3 and negative 1, we'll choose like negative 0.8. Between 0 and negative 2/3, maybe we'll choose negative 0.2. Between 0 and 5, I don't know, we'll choose 2. And over here, we'll choose positive 1,000 to get our end behavior. Okay, so we also need to investigate what happens near the critical values where the function is undefined. We have to see what happens. Even though x can't be negative 2/3, it can be really close. So we're going to use the calculator to investigate that as well. So let's start with our left end behavior. The first thing I want to do is store negative 1,000, store it for the x variable on my calculator, and hit enter. Now I need to type my function, which is a fraction. So I'll enter my fraction button, And on top I've got negative x squared, parentheses, x plus 1, parentheses, open parentheses, x minus 5, close parentheses. And on bottom, I've got 3x plus 2 times x minus 5. And so when I hit enter, it's going to calculate the value of that function for the x value that I've got stored, which is negative 1,000. And we can see we get a really big negative number, negative 333,000. So that seems to say that this function is going to go to negative infinity on the left end. But just to verify that, let's plug in an even bigger negative x value, like negative 10,000. Let's store that for x. And now calculate the value of the function. We should get a bigger negative value than negative 333,000. And we do, quite a bit bigger. So that seems to confirm that our function is going to negative infinity on the left end. So for our left end behavior, as x goes to negative infinity, y also goes to negative infinity. Okay, let's go ahead and investigate our right end behavior as x goes to positive infinity. So now I want to store, let's say positive, let's do 10,000 for x. So 10,000, store x, go up and find our function, select it and hit enter again, and it calculates the value of our function whenever x is positive 10,000. And again, we get a really big negative number. So even on the right end, as x goes to positive infinity, y still goes to negative infinity. Okay, so now let's go ahead and look at our middle behavior here. Let's plug in negative 0.8 for x. So I'll type negative 0.8, store that for x, enter, go up and highlight our function that we've already typed once, hit enter to retype it, and enter one more time to calculate the value, and we get positive 8/25. So that's a positive number. And for the middle, that's all we're concerned with, is whether it's positive or negative for now. So in this region, we get a positive number. Now let's look at negative 0.2. So we'll do negative 0.2, store for x, go highlight our function, select it, and calculate. We get negative 4 over 175. So there we get a negative output. So we'll put a negative output in that region. Now let's plug in 2. Okay, so we'll do 2, store x, go highlight our function and recalculate it, and we get negative 3/2. So we get a negative output when x equals 2. Okay, now what we need to do is investigate more thoroughly what happens whenever our output is undefined. So I need to look at both sides of negative 2/3 and see what happens to y, and both sides of 5 to see what happens to y. Let's do 5 first, since it's easier, it's not a fraction. So I'm going to plug in maybe like 4.99999 on the left side to my function, and I'll plug in something slightly bigger than 5, like 5.000001, and see what happens. So to the left side of 5, I might plug in 4 point, and I'll just put several 9s, store that for x, and then calculate the output of my function for that value that's really close to 5. And you can see we get like negative 8.8. That's interesting. So negative 8.8. Now let's see what happens if we plug in something slightly bigger than 5, like 5 point, I'll put a lot of zeros, followed by a 1, store that for x. And we get about the same value, about negative 8.8. So what's happening here is that as x gets close to 5 from both sides, the y value is actually getting really close to negative 8.8. But when it gets to 5, it can't be defined. So what happens here is we'll have a hole in our graph. and it will occur whenever x is 5, and the y value is going to be about negative 8.8. So we'll see how that looks when we graph it. So that's interesting. Let's see what happens when we get really close to negative 2/3 from both sides. And remember, negative 2/3 is negative 0.6 repeating. So if I want to go from the left, I need to be like negative 0.6666667. If I want to be to the right, I might just do negative 0.6666666. Not going on forever. So let's look to the left of negative 2/3. So I might do negative 0.6666, a bunch of sixes followed by a 7. That's slightly to the left of negative 2/3. Well, oh, I forgot to store that for x. Now we'll go up and we'll recalculate the output of our function, which is already typed. Oh, and it has a divide by 0 error, even though we're not plugging in negative 2/3. So calculators have limits on what data they can process. So let's do this. Let's clear that out and go back up and let's type, let's see here. Let's not make it so close, negative 0.6667. Let's try that. That's slightly to the left of negative 2/3. Store that for x, and let's calculate the output of that. There we go. So we get 1,481. We get a pretty big number there when we're slightly to the left of negative 2/3. Let's get even closer. Let's do negative point. Instead of 3 sixes, we'll do 4 sixes. Negative 0.1234 sixes followed by a 7. Store x. Let's see if it can handle that. We get 14,000, an even bigger positive number. So something different is happening near 2/3 or negative 2/3 than happened at 5. At negative 2/3, we're getting, from the left side, we're getting really big positive numbers. So our graph, our values are going to be positive, and they're going to get really big as we get close to negative 2/3. So we're not getting close to some fixed number like negative 8.8. It's growing without bound. Let's look to the right of negative 2/3 and see what happens. So this time I'll use negative 0.666. That's slightly to the right of negative 2/3. We'll store that for x. Calculate the output of our function. And we get negative 74. Okay, so now we get a negative number. Let's get even closer to negative 2/3. Let's do negative 0.66666. Store that for x. And recalculate our function. So we get negative 7,407. So as we get closer to negative 2/3 from the right, we get really big negative numbers. So it's going to be going down as it gets close. Let's see what happens when we put all of this onto a graph. Okay, so 0. Let's go ahead and mark all of our zeros and critical values. So we've got negative 1, negative 2/3, 0, and then 5's way over here. And negative 1 outputs a y value of 0. That means it's an x-intercept. Negative 2/3, we can't hit negative 2/3, so I'm not going to do anything there yet. 0 outputs 0, so it's an x-intercept. And 5, we have a hole in our graph at 5, negative 8.8. I'll just put that down here like this, and I'll label it with the ordered pair 5, negative 8.8. It's approximate, by the way, so I'll say it's approximately 5, negative 8.8. Okay, so that's a hole, not a 0. Now let's look at our graph. To the left of negative 1, our graph goes to negative infinity. After negative 1, our y values are positive, and then as x gets close to negative 2/3, it goes up forever. So it does this kind of thing. Y goes to positive infinity. What that means is we have what's called a vertical asymptote here. This sort of imaginary line that we can't cross, we just get infinitely close to. So on the left side, as we can see from our sign chart, I have to go to negative infinity as I get close to negative 2/3 from the right. So from 0 to the left, my y values are negative. And as I get close to negative 2/3, I go to negative infinity. Now between 0 and 5, I'm negative, but I know I'm going to get close to negative 8.8 as I get close to x equals 5. And then from there, I go to negative infinity. So it's going to sort of cut through my ordered pair and go down like that forever. So some interesting things happen here. When your function is undefined, you could get an asymptote, or you could get a hole. So let me talk to you about some shortcuts. You can always use the calculator, which works faster than you might think. I'm just making a video, so it takes a little while. But you can, whenever you have a rational function where something on top cancels with something on bottom, you might have a hole at that critical value, like here, 5. Whenever it doesn't cancel, you get this vertical asymptote. And that's pretty simple. You can use a calculator to verify that. Now, how can you get the rest of this without using a calculator? Well, you can get the end behaviors by looking at the leading term. The leading term, well, if you multiply out the top, you get negative x to the 4th. If you multiply out the bottom, your leading term is 3x squared. And if you simplify that, your coefficient is negative 1/3, negative 1 over 3. And then if you cancel your x's, x to the 4th divided by x squared is x squared. Well, negative 1/3 x squared is an x squared flipped over. So both ends point down like this. And you can see that matches what we have here for our end behavior, and it also matches the end behavior on our graph. And then once you know your end behaviors go to negative infinity, then you can use your multiplicities to get your signs. So an odd multiplicity means we have a negative infinity output over here. If we have an odd multiplicity, that means the output sign of negative will change to a positive output sign here. Negative 2/3 has an odd multiplicity, so the output sign changes again to a negative. 0, though, has an even multiplicity, so the sign stays the same. And 5 has an even multiplicity, so the sign stays the same again. So you can put all those pieces together and generate the sign chart quite a bit more quickly, but you really have to understand this leading term business to get the end behavior. Let's do some more examples where I won't walk through everything in the calculator. And we're still going to sketch the graph using end behavior and the sign chart. In this case, we'll look at the function f of x equals the fraction where the numerator is 3x cubed minus x squared, and the denominator is 2x plus 1. Now, unfortunately, this guy is not factored, so let's go ahead and factor it here so that we can find our zeros and critical values. On top, we can pull out an x squared, leaving behind a 3x minus 1. And on bottom, we just have 2x plus 1. Now we have enough to make our sign chart. So we can go ahead and mark the zeros and critical values. We've got 0, 1/3, and negative 1/2. Negative 1/2 comes first. It has a multiplicity of 1, and since it makes the denominator 0, the function is undefined. Furthermore, without using a calculator, we know this is going to be a vertical asymptote because 2x plus 1 doesn't cancel. Our next critical value, or 0, is, let's see, 0, multiplicity 2, and that makes the numerator 0, so the whole function is 0. And finally, 1/3, multiplicity 1, makes the numerator 0, so the whole function is 0. Now we can use a calculator to do this, but I'm going to walk through finding the end behavior and the signs with the leading term and the multiplicities. So my leading term here on top is 3x cubed, and on bottom is 2x, which reduces to a coefficient of 3/2 times x squared, which means both ends go to positive infinity. So as x goes to negative infinity, y goes to positive infinity, and as x goes to positive infinity, y also goes to positive infinity. So on my left end, I've got positive infinity, and my right end, I've also got positive infinity. Now, negative 1/2 has an odd multiplicity. That means the signs on either side are going to be opposites. Since this is positive, my next sign is negative. 0 has an even multiplicity, so my next sign will be the same as the previous, which is a negative. And then 1/3 is an odd multiplicity, so the sign changes, and we're in good shape. Now let's see if we can put together the graph. Understanding that we have an asymptote at -1/2. At 0, we have an x-intercept, and at 1/3, we have an x-intercept. Also, we know what the ends look like. A lot of people forget the ends. So to the left, we have to go to positive infinity. And then as we move to the right, we can't just stop here. We have to go all the way to -1/2, but not touch it. We know that when you have a vertical asymptote, you're either going to deflect up as you get close, or you're going to deflect down. Well, we know that this portion of our number line chart outputs a positive sign. So I can't go below the x-axis. So my only choice is to deflect up. And if you're unsure about this, plug in a number really close to -1/2 from the left, like -0.50001, and see that you get a really big positive number. In my next region, I have to be below the x-axis from 0 and between 0 and -1/2. I've got to be at 0 here and then go to -infinity as I get close to -1/2 from that side, because I can't deflect up without crossing the x-axis. Between 0 and 1/3, I have to be below the x-axis, but there's no asymptote, so I just touch the x-axis again. And then after 1/3, I go to positive infinity. And so that's how to do this without using a calculator. We've got a few more examples to make sure you're comfortable with all of this. Let's keep going. Okay, let's continue to sketch the graph using end behavior and sign chart. This time, let's look at the function g of x equals the fraction, where the numerator is -3 times x plus 5 squared times x minus 6 to the 4th, and the denominator is x minus 2 times x plus 2 squared. All right, oops. The good news is this guy is factored, so we can quickly find our zeros and critical values. So we know we have 1, 2, 3, 4 zeros and critical values. -5 is the first one with multiplicity 2. It's from the numerator. Then we've got -2 is next with multiplicity 2 from the denominator. So we get an asymptote. And then we've got +2 from the denominator has multiplicity 1, another asymptote. And then we have +6 from the numerator, multiplicity 4. Okay, so now we need to know the end behavior. Again, use a calculator or use the leading term. The leading term on top will be -3. Let's see here. Let's write this out differently. Leading term on top of -3 times x squared times x to the 4th. So that's x to the 6th. On bottom, I've got x times x squared. That's x cubed. That reduces to -3x cubed. So the left end is going to grow in the positive direction. The right end is going to grow in the negative direction. So as x goes to -infinity, y goes to positive infinity. And as x goes to positive infinity, y goes to -infinity. All right, multiplicities are even, so we keep the same sign. Even again, still positive. Odd multiplicity, so the sign changes. Even multiplicity, so the sign stays the same. So number line chart's done. Let's graph it. We got -5 as an x-intercept, -2 as an asymptote, because that factor didn't cancel. +2 is another asymptote, and +6 is an x-intercept. Let's go from the left to the right. We've got -5 left. We have to be positive and go to positive infinity. Between -5 and -2, we have to be above the x-axis, but we have to approach the asymptote as we get close. Between -2 and 2, we have to be above the x-axis and approach both asymptotes. So I have to do this in the positive direction, and I have to do this in the positive direction. And then I'm just going to connect those without touching the x-axis because I have to stay above the x-axis. Between 2 and 6, I have to be negative and approach my asymptote. And then after 6, I have to be negative and go to negative infinity. And there we go. Let's do 3 more. Let's see, yeah, 3 more. Okay, so the function here is f of x equals the fraction 2x cubed minus 12x squared plus 18x over x squared minus 9. And unfortunately, this time the polynomials are not factored. And I don't want to bore you with how to factor these. I'll just say, okay, well, if you do factor, you end up with, on top, 2x times x minus 3 squared over x plus 3 times x minus 3. Okay? And so now we have our zeros and critical values. Let's go ahead and make our sign chart. So here we've got 0, positive 3, negative 3, and positive 3 again. We've got some cancellation going on here. So let's see what happens there. But negative 3 comes first, has multiplicity 1, and it makes the denominator 0, so it's undefined. Then we have 0, which is multiplicity 1, makes the numerator 0. And we have positive 3, which makes the numerator and denominator 0, but since it makes the denominator 0, the function's undefined, and it has a total multiplicity of 3 because it shows up twice in the numerator and once in the denominator. All right, now, if you do cancel x minus 3 here, it's not gone completely. It still remains in the numerator. So this is one where you might want to investigate with a calculator what happens really close to 3. But we know negative 3, we're going to have an asymptote. Okay? Now let's look at our leading term to get our end behavior, or you could use a calculator. I've got 2x cubed over x squared, which reduces to 2x. So the left end goes to negative infinity. The right end goes to positive infinity. So I'll put those in. And then I'll use my multiplicities to get the middle signs. An odd multiplicity means my sign of negative changes to a positive. Odd again, positive changes to a negative. Odd again, negative changes back to a positive. Now, what I find when I look at my calculator is if I plug in numbers really close to 3 from both sides here, I do not get really big numbers. Instead, I get like 0. So here I have a hole at the ordered pair when x is 3, y is 0. That's interesting. So I have an asymptote here, but over here, even though I canceled, I had a hole in my graph. I have a hole in my graph because of the cancellation. So let's look at the graph of this. Negative 3, 0, 3. The negative 3, we have an asymptote at x equals negative 3. At 0, we have an x-intercept, and at positive 3, we have a hole at the ordered pair 3, 0. All right, now we just fill in the behaviors. To the left of negative 3, I have to go to negative infinity, which means as I get close to my asymptote, I have to stay negative and approach negative infinity as well. I have to be above the x-axis between negative 3 and 0, approaching my asymptote. And then between 0 and 3, I have to be negative. And then after 3, I have to go to positive infinity. There's another great example. We've got a hole, an asymptote, and an x-intercept. Let's do another. So the function we'll graph this time is f of x equals the fraction where the numerator is x squared plus 2x plus 1. The denominator is x cubed plus 3x squared minus 25x minus 75. Again, unfortunately not factored, and I, again, won't spend time factoring it for you in the video. I'll just say if you do factor it, on top you get x plus 1 squared, And on bottom, you get x plus 5 times x minus 5 times x plus 3. And so nothing cancels, so we're not going to have any holes in the graph this time. We'll just have asymptotes. So we've got 4 zeros in critical values, the first one being -5, multiplicity 1. Then we've got -3, multiplicity 1, -1, multiplicity 2, and +5, multiplicity 1. -1 is the only one in the numerator, so that's going to give us an output of 0, and all the others are going to give us undefined outputs, resulting in asymptotes on our graph. The leading term on top is x squared, on bottom is x cubed, which reduces to 1 over x. So here, the left side is going to get close to 0 from the negative side, and on the right, we're going to get close to 0 from the positive side. So as x goes to negative infinity, y is going to approach 0 from the negative side, and as x approaches positive infinity, y is going to approach 0 from the positive side. So I'll have 0 from the negative side, 0 from the positive side. And then multiplicity odd, so I'll have a positive output here. Odd multiplicity, sign changes to negative. Even multiplicity, sign stays the same at negative. Odd multiplicity, it changes. Let's give this guy a graph. -5, -3, -1, and +5. -1 is an x-intercept. All the others are vertical asymptotes at x equals -5, -3, and +5. When I'm to the left of -5, I have to get close to 0 from the negative side. And as I move right, I have to get close to my vertical asymptote. So I've got to do this. Between -5 and -3, I have to be above the x-axis and approach both asymptotes. So something like that. -3 to -1, I have to be negative and approach my asymptote. Between -1 and 5, I have to be negative and approach this asymptote. And then after 5, I have to approach 0 from the right side, like this, and then I have to approach my asymptote as well, so I have to do that. Now in this case, what we have when you're getting close to 0 is we have a horizontal asymptote. Our graph is getting really close to the horizontal asymptote of the line y equals 0. So we have 3 vertical asymptotes at x equals -5, -3, and +5. But we also have a horizontal asymptote for our ends at y equals 0. All right, our final example. Sorry about all the examples, but there's so many different things that can happen with rational functions. Let's graph where the numerator is x plus 5 squared and the denominator is 3x minus 8 times x plus 7. No cancellation, so no holes this time. Let's draw our sign chart. We have 3 zeros in critical values. -7 is first. Multiplicity 1 makes the function undefined. Then we've got -5. Multiplicity 2 makes the function equal 0. And we have +8/3. Multiplicity 1 makes the function undefined. The leading term on top is x squared. On bottom, it's 3x squared, which simply reduces to 1/3. So on both ends, we're going to approach +1/3. It's interesting. If you look at that on a graph, just locate 1/3 on the y-axis, and both ends are going to approach this line, y equals 1/3. All right, so we have another horizontal asymptote at y equals 1/3 in this case. And if you did this end behavior in your calculator, you'd probably see that you're getting really close to 0.33333 repeating on both ends. if you plugged in like negative 10,000 for x or positive 10,000 for x. That's what that would mean. All right, let's get the rest of the signs. We got a positive here, then an odd multiplicity, so we have to change to a negative. Even multiplicity, we're going to stay negative. Odd multiplicity, we're going to go back to positive. Now we can graph it up. -7 is a vertical asymptote, x equals -7. -5 is an intercept, and 8/3 is a vertical asymptote at x equals 8/3. Then we better go ahead and mark a y value of 1/3 and sort of draw in this horizontal asymptote to help us with our end behavior. So to the left of -7, my end is going to approach 1/3, and as I go to the right, I've got to approach my asymptote. And I have to stay above the x-axis. I can't cross it. So this is my only choice. Between -7 and -5, I have to be negative and approach my asymptote. Between -5 and 8/3, I have to be negative and approach my asymptote. And then after 8/3, I have to be positive and approach both asymptotes. And there we go. We got horizontal asymptotes, vertical asymptotes, and we've got holes. Okay, so different types of end behaviors, different types of behaviors near critical values. Use your calculator when necessary. Be fluent with all the different techniques, and you should be good with this. It takes a lot of practice, but once you get it, it gets pretty fun because every graph is a new challenge. Every graph is like a new puzzle. Do some practice, get good at it, have some fun.